The curved arrow is probably the most important arrow in organic chemistry. Stay tuned as I teach you the ninja level rules you need to know. The curved arrow is our key storytelling device in organic chemistry. It is the blueprint to every mechanism, every structure, and every resonance contributor that you draw in this course. The curved arrow tells us the story of what happens. It tells us the story of every old bond being broken and every new bond being formed as we turn starting materials into products. Curved arrows are not random. They are not just glyphs on a piece of paper. They are very intentional and they tell a very purposeful story. Before we go much further, let me clear up one very important point. Only electrons move in organic chemistry. When students fundamentally don't understand what's going on in organic chemistry, it often results from this. Only electrons move in organic chemistry. Atoms don't move, bonds don't move, charges don't move in organic chemistry. Only electrons move in organic chemistry. Now, atoms may change places, and bonds may change places, and charges may change places as a result of electrons moving, but only electrons move in organic chemistry. If you're going to do something in organic chemistry, it's going to be because electrons moved, not bonds or atoms or charges. Cannot emphasize that enough. You have to understand that fundamental tenet for this course. The curved arrow then tells a story. It tells a story of the movement of electrons. Specifically, it tells the story of the movement of two electrons. This type of curved arrow tells the story of two electrons moving in organic chemistry. There are other types of arrows, some that show the movement of one electron. This isn't a video about those types of arrows. I have a different video down below where I go through all of the arrows in organic chemistry. Curved arrow always starts at an electron source. It always starts at an area of high electron density. In order to tell the story of the movement of electrons, we have to start the arrow at a place of electrons. One of our tasks on the road to becoming an OChemNinja is to look at a molecule or a series of molecules and find those places of electron sources. Here is a list of common electron sources in hierarchy order. The best place to find an electron source would be a lone pair, specifically if that lone pair is involved with a negative charge. A next great place to find an electron source is at some kind of pi bond. The pi bond is a sharing of electrons. A single bond is a sharing of 2 electrons. A double bond is a sharing of 4 electrons. 4 is more than 2, so a pi bond is an area of excess electron density. It's an electron source. And finally, on some occasions, you can start an arrow at a sigma bond. It's not the best place to look for excess electron density, but it is a valid place to start an arrow, with the caveat noted below that we can never start an arrow at a single bond if we are drawing resonance contributors. If you're just learning resonance, I have an entire playlist on resonance in the description down below. Once we've identified where we're going to start a curved arrow, we have to figure out where we're going to point that curved arrow. Curved arrows always point to some kind of electron sink. An electron sink is some place in a molecule that can accept a pair of electrons. It's someplace that somehow lacks electron density in the molecule. Sometimes we'll point arrows at an electron deficient atom that can use more electrons. Sometimes we'll point it at the bond between two atoms to form a new bond between those atoms. Common places we can point arrows then is to an adjacent bond. If we start at this lone pair, we can draw an arrow to an adjacent bond. We can't draw an arrow to any random bond in the molecule, but a valid curved arrow could point the arrow at the adjacent bond. We can also point the arrow at a constituent atom. What I mean by that is if we start the lone pair at the pi bond, we can point the arrow at one of the atoms involved in that pi bond, either the oxygen or the carbon. Oxygen is more electronegative than carbon, so it's likely to point to the oxygen, but a valid curved arrow could draw the arrow from the pi bond to one of the constituent atoms. We can't necessarily draw it to any random atom in the structure, but one of the constituent atoms is a valid curved arrow. Finally, we can point the arrow at an electrophile. This isn't a video about nucleophiles or electrophiles. I have a separate video that I'll link to down below. But if we start this arrow at a sigma bond, we could point it at the electrophilic carbon atom in this other molecule. To do so, we would start the arrow at the sigma bond. We would bounce this arrow through the carbon atom. When we break this carbon-magnesium bond, it's the carbon atom that will do the attacking, and this carbon atom will attack the electrophilic carbon of this aldehyde. This would be an example of a curved arrow pointing to an electrophile. This arrow shows an example of bouncing arrow notation. If you're not familiar with bouncing arrow notation, check out my other video down below to learn more about bouncing arrows. These are examples of valid places that a curved arrow can point. I'll mention again that in this last case, we're pointing it at an electrophile. That's a valid curved arrow, but if you're in resonance land, you cannot point arrows at electrophiles in resonance. That's not part of the resonance contributors. In resonance land, we'll only be pointing arrows at adjacent bonds or constituent atoms. As we wrap up our discussion of the rules for curved arrows, we must always remember that curved arrows must obey the octet rule. Curved arrows are the blueprint for the molecular transformations that happen in organic chemistry. They tell you exactly what to change about an original structure in order to draw the next structure. Arrows tell the story. They tell the story of the movement of electrons. They tell the story of old bonds being broken and new bonds being formed. This isn't a video on using curved arrows to tell a story. I have a video that I'll link to down below. For example, in this first structure here, the arrow starts at the lone pair of electrons and points to the adjacent bond. This is telling a story. It's telling the story that we're taking this lone pair that used to be localized on this carbon, and now we're sharing it between these two carbon atoms as a new bond. It tells us the story of old bonds being broken and new bonds being formed. We're forming a new bond between these two carbon atoms. We need 2 electrons for that bond. Where do we get those 2 electrons? From the lone pair on the adjacent atom. The atom shares its lone pair with the adjacent carbon to form a new carbon-carbon pi bond. But as drawn, this would violate the octet rule. This would form a new pi bond here, which would ultimately give us 5 total bonds around carbon. You can't have 5 bonds to carbon. Actually, not such a big deal. This happens all the time in organic chemistry. When we get to a place like this, that's not a big deal. We just need another arrow to help us continue the story. If the result of this arrow would form 5 bonds around that carbon, then we're going to need another arrow to ensure that we don't end up with 5 bonds around carbon. To do that, we'll draw a second arrow. To add a second arrow, we have to be sure we're following the curved arrow rules for multi-arrow systems. Electrons flow in organic chemistry. They start at an area of high electron density and they flow to an area of low electron density. They start at an electron source and they flow to an electron sink. In this way, you can kind of think of them like pressure or temperature. They start at a high pressure and flow to a low pressure. Start at a high temperature, flow energy to a low temperature. Start at a high electron system and flow electrons to a low energy system. So when we draw our curved arrows to represent that flow, we have to keep a couple things in mind. 2 arrows can't start or end at the same place. If I draw this arrow from this lone pair to the right, I can't also take this lone pair and do something over on the left side of the molecule. Those 2 electrons can't go in 2 different directions at the same time. That would be violating the curved arrow rules. Similarly, I can't have another pair of electrons point to the same position. If I'm forming a bond between these 2 carbons, I can't form another bond with the same set of arrows. The way we will reconcile this for this particular system is to follow our curved arrow rules. We'll start our second arrow at a place of high electron density. That would be the pi bond between carbon and oxygen. And we'll flow those electrons to a place of low electron density. That would be the constituent atom, the oxygen atom. You can't point it down to the carbon. That would be 2 arrows pointing towards the same place. Arrows can't double back on themselves. We can't start flowing electron density one direction and then all of a sudden jump back into some other direction. Instead, we'll continue the flow of electrons by breaking the pi bond and putting those electrons onto the constituent oxygen atom. That will form what will end up being a resonance contributor for this enolate anion. That forms the other resonance contributor for the enolate anion with a double bond between the 2 carbons as a result of this first arrow. The second arrow says we're taking the electrons that used to be shared between the carbon and oxygen and localizing those electrons onto oxygen as a new third lone pair. Notice the negative charge ends up on oxygen as a consequence of the curved arrows moving. Notice there is no arrow moving the negative charge over to the oxygen. That's not something you can do with curved arrows. That violates the curved arrow rules. As a result of these electrons moving, this carbon becomes neutral and the oxygen becomes anionic. Only electrons move in organic chemistry. There aren't any other arrows needed for this system. The consequence of these arrows won't violate any chemistry bonding rules. The result of these arrows will be the resonance contributor for this original structure. In the resonance sequence for this protonated carbonyl, the electrons start at the pi bond and get localized onto the oxygen as a new lone pair, from 1 lone pair to 2 lone pairs. In order to break this pi bond and put the electrons on oxygen, we had to take the electrons away from the carbon that it was sharing with. So when we draw the new resonance contributor, the carbon that we used to be sharing electrons with is now fully positive, fully cationic. Notice there's no curved arrow moving the positive charge down to this carbon. Charges can't move in organic chemistry. Only electrons move. As a result of breaking the pi bond and putting electrons on oxygen, oxygen became neutral, but we took electrons away from carbon, so carbon became cationic. In this final example, we will need 1 more curved arrow. The result of this arrow would be a new carbon-carbon bond and 5 bonds to that carbon. We can't have 5 bonds to carbon. We're going to treat this much the same way we treated the first example. We'll start an arrow at the pi bond and point those electrons directly to the oxygen. This arrow says we're taking the electrons that used to be shared between carbon and oxygen and depositing them locally onto oxygen as a new lone pair. Go ahead, pause the video, see if you can draw the product that results from this blueprint from these curved arrows. Is this the structure that you drew? This can be tricky based on these curved arrows. Let me walk you through what's happening. Curved arrows tell the story. They tell the story of the movement of electrons. They tell the story of old bonds being broken and new bonds being formed. This first arrow says we are breaking the carbon-magnesium bond. Carbon is no longer bound to magnesium. Instead, carbon-2 is using those electrons to form a new carbon-carbon bond with carbon-3. This carbon-2, carbon-3 bond consists of 2 electrons. It consists of the 2 electrons that used to be in the carbon-magnesium bond. Carbon got to keep those electrons and form the new bond with carbon-3. Where did magnesium go? The carbon-magnesium bond broke and magnesium dissociated as a magnesium cation. Forming the bond between 2 and 3 would have been a 5th bond to carbon number 3, built up too much electron density around carbon 3. So we'll break the carbon-oxygen pi bond and push those electrons onto oxygen as a new lone pair. That gives oxygen a full negative charge. Notice I don't have an arrow going from the bond to magnesium. 2 arrows can't start at the same place and point in different directions. Magnesium doesn't get to keep the electrons. Magnesium doesn't leave with a lone pair. Magnesium leaves as a cation, missing electrons. Where do those electrons go? They stay with carbon-2 to form the bond with carbon-3. Again, these are arrows in the context of a reaction, not in the context of resonance, but we're going to see arrows very similar to this throughout the rest of the course. Now you know what a curved arrow means and how to use it like an OChemNinja.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.